Hello, everybody, and welcome to episode 88 of the Hyperthesis podcast. I'm Liam.
I'm Feely. I'm Patrick.
I'm Billy.
Yes, Billy, welcome. As you can hear, everybody, we have a very special guest with us today, Billy Sievers. Thank you for coming, Billy. It's great to have you.
Oh, yeah, anytime.
So, just a little introduction on Billy. Um, Billy Sievers is a second-year Ph.D. student at McMaster University who works with Dr. Hari Kunduri. Billy completed his Bachelor of Science at the University of Calgary, where he studied near-extremal horizons and black holes with Sean Stoyton? I'm sorry, is that how you pronounce it?
Oh, Stotine.
Stotine, okay, Sean Stotine. So that's who you did your undergraduate research with, and you completed your Master of Science at Memorial University in Newfoundland and Labrador, where you studied self-intersecting surfaces inside black holes with Ivan Booth and Roby Hennigar. Did I pronounce that correctly?
That's right.
Perfect. So Memorial's kind of close to where we did our undergrad, so we're at least the three of us are aware of it. We did ours in Nova Scotia, as we've probably talked about a bunch before. But right now, not about the past, but the present. You currently work at McMaster University, where you're continuing your research with self-intersecting surfaces inside black holes and connections to quantum gravity, primarily through ADS and CFT correspondence, which will get you to tell us what that means later. But for now, we'll go to an intro topic, which I have also prepared. So, the intro topic is related to black holes, maybe not so much quantum gravity. Well, maybe a little bit, depends. But I found this article online. It was titled "Extraordinary Trinary Black Hole System is the first of its kind ever found." So it was published on October 2024 on ScienceAlert.com. It was like it wasn't, there was a paper on it, but the article I found was like someone just kind of reviewing the paper or talking about it in kind of more layman terms. And before I talk exactly about it, a little bit of background information on it. So there's a constellation called Cygnus, which is roughly 7,800 light years away from us. And there exists a black hole of about 9 solar masses, so about 9 times the mass of our own sun. And within this, within Cygnus, there's a system called V404 Cygni. The system, it possesses this 9 solar mass black hole, but it also possesses a giant star with a mass a little bit less than our own sun, so a little bit less than a solar mass. So therefore, it's a binary system. There's a black hole, there's a star, they kind of orbit around each other. That's what they call a binary system. And they orbit each other with about a period of about 6.5-ish Earth days at a fairly close range. So they do a complete rotation every 6.5 days, and they're quite close to each other. And because of this really close proximity and the intense gravity that happens when you're near a black hole, the star that orbits the black hole, it repeatedly loses mass. So kind of like mass gets sucked out of it into the black hole and into the black hole's accretion disk. And so because of this, the star is known as a variable star because it repeatedly kind of gains and loses intensity. It like kind of shimmers a little bit. So if you're an astronomer looking at it, you'd see it get brighter and then dimmer and then brighter and then dimmer. And pretty sure that's due to the orbit, the close proximity of the orbit with the black hole. Not 100% sure, but that seems to make sense to me. Also, the star is also known as a nova star because it periodically emits large amounts of energy and is a soft X-ray. It's soft X-ray transient, which basically just means that it periodically shoots out short bursts of X-rays. So already this binary system's kind of pretty interesting. It's a star orbiting a black hole. They're very close to each other. Some interesting things happen when you have a system like that. But where does this article come in? The article that I told you it's a binary system, but the article had the word trinary in the title. So a paper that was published on October 23rd, 2024, titled the black hole low mass X-ray binary V404 Cygni is part of a wide triple, which is the paper that the article I found talks about. And the scientists in this paper found that V404 Cygni also contains an unseen binary companion or a third body. So it's now people believe it's now a trinary system. There's three bodies orbiting each other. They found this kind of like hidden star that has on a very wide orbit of around 70,000 years. So there's a binary system that orbit each other every 6.5 days, and then there's this really far away third star that orbits them every 70,000 years. So it's quite far away. And it's the first instance of a system of stars and black holes of this configuration that scientists have found. And it can help us learn a lot about black hole formation potentially, which is a major problem in astronomy and cosmology. I don't know if you study any of this, Billy, but I know there's a lot of people who study like how black holes form, because you can think of like, a star goes supernova, it collapses and it blows up, or there's this thing called like I think it's called like an instantaneous collapse where you don't get like an explosion. It's kind of like everything just sucks in and you suddenly have a black hole. But there's lots of different types of masses of black holes. There's small black holes, which are of the order of a few solar masses, and then there's these big supermassive black holes, which are at the center of galaxies. But then you can have like medium range black holes. And there's lots of people who study like how they form, because some models of formation work for certain ranges of masses and some work for others and some don't. And I'll get into that in a second, but I just wanted to see if I don't know if any of that stuff shows up in your work or if it's in papers you read about or what.
Yes. So definitely outside of my field expertise here, but hilariously enough, I know a bit about this just because here at it's at McMaster, the astronomy part of the department there is quite large and quite competent and very wide in variety as well. So hang out with them, um, going out to lunches with them, and once in a while you sort of they it's annoying. Maybe you haven't had this yet, Liam, but they try to group us in with them. They say, "Oh, hey, black holes are astrophysical, so you're an astronomer. Basically, you're an
Yeah,
astrophysicist."
I've had
Like,
that happen to me once or twice. But like
right?
I'm even like kind of more far removed from it than you are.
That's right. Yes. So I mean, and I keep trying to tell them, "Hey, listen, all my black holes are perfect models. All right, they're in isolation. Stay away. No accretion disk. Like, go away." Um, so on the different masses, yes, there's actually uh there's a group at the University of Calgary led by Dr. Matthew Taylor. He tries to find. He's using, I think, JWST data to try to confirm or try to sort of reason um, finding intermediary mass black holes at the center of globular clusters, um, sort of these tight, compact star clusters. Um, and and you're right. I sort of asked some of the astronomers here in at McMaster, hey, is this intermediary mass black hole idea, is that just a meme? Do you guys laugh at that, or how feasible is it really? Because it also sounds like in order to sort of get those sort of black holes to be out there, um, you need to accept the idea of primordial black holes for those to have been the seed
Hmm.
to eventually become that. So yeah.
Yeah, I think maybe I've mentioned primordial black holes once or twice, but they're like very tiny black holes that are kind of theorized to have formed in the early universe or something. Like, like black holes with a radius of like what, like centimeters or less kind of thing. Yeah. So people are really interested, especially intermediate mass black holes, because they're very rare. We don't see many of them. So it's like what happened to them, right? But then I think we have found a small amount of them. So it's like how did they form? Our current models don't really explain that. But this trinary system, this V404 Cygni, it has like a 9 solar mass black hole, which you would consider like a small black hole, not an intermediary one. Um, but based on this three body system, you would expect you would expect that you can't have a three body system if this black hole formed through a supernova, which is like the commonly accepted kind of way that small black holes form. Yeah, let me just go back to my notes quickly because I forgot where we were, but in my thought process. Oh, okay, yeah. Yeah, it's typical stellar mass black hole forms via supernova. Like you have a really big star, it runs out of its own fuel, collapses under its own weight, and if it's big enough, you can form a black hole. That's how you form. That's like the leading theory, I think, for small black holes. A few solar masses. But for the case of the V404 Cygni trinary system, if the black hole formed through that usual mechanism, it surely wouldn't have allowed this third body orbiting it to exist in such a wide orbit. It would have caused this third body, this third planet or rock, or I don't even know what it is actually. They don't really mention it in the article, but they might not know. They just know it's something with mass. Um, but if this black hole formed through supernova, it would have caused kind of this like instability, and this third body would have shot out into space, and it wouldn't be doing this super large orbit. Um, if you know anything about classical mechanics, and we've talked about it a little bit before, but three body systems are chaotic typically. And you can argue like chaotic just means they're not very stable. They're very sensitive to initial conditions, so a very small change of something has a large effect many years later. So basically, if a supernova causes black hole, you would expect that you wouldn't have a trinary system. So how did the black hole form? It kind of brings into question the currently accepted models. Like, are there other ways black holes, less violent ways they might form? This possible direct collapse model, where a black hole just kind of simply collapses on itself and forms a black hole in a non-messy way without a big supernova explosion. Maybe that is something that can happen.
Well, how sure are we that that's a trinary black holes? Is a trinary system? Because to me, like black holes are kind of hard to find, right? And well, I mean, you cannot see it directly. So is there a margin of error that's acceptable? That's like, well, it's definitely the three things revolving around one another, or like, is there real evidence of this?
I know that the binary system, so the black hole and the star that are very close, that's like pretty well known. I don't think there's any debate there. This third body, it turns out that people have known about this third kind of body that's orbiting around it for a long time, but they thought it had nothing to do with this binary system. They thought it was just something that was nearby. But then they realized that this paper goes and does a bunch of calculations and simulations and stuff. And they realize that it's actually moving with the binary system. So it's considered like a third body. It's in the orbit, even though it's a very, very weak gravitational coupling. I think that they're confident. Again, like you said, how confident are they? How much margin for error is there? I don't know. But they're confident enough that they're claiming, they're not even like saying it's possible. They're just straight up like claiming that it's the case.
Yeah, just like how the room temperature superconductor was claimed, right? And that became a big news for I don't know, a couple of days or a couple of weeks. It's kind of hilarious.
Yeah, so I mean, if they're claiming something and it's not, it's obvious that like maybe they did something wrong, people are very quick to call it out. They have peer reviews. It made it through peer review into a journal. Like, odds are they've got some good evidence backing them up. But yeah, that's always the case in science, right? Like, you can make a mistake, people get ahead of themselves.
So this kind of just talking about three bodies reminds me of a video I watched recently from the Minute Physics channel. For those that know about it, I would recommend checking it out, especially if you don't know about it. But he did a very interesting video, essentially looking at the Earth, Moon, Sun system as essentially just a fancy type of three-body system. And it's really funny because it's looking at essentially the orbit of the moon around the sun instead of looking at how the moon orbits around the Earth. Because if you look at it, you remove the Earth from the equation, it just has a very funny orbit around the sun. But it's essentially a three-body problem that's stable. But that being said, the gravitational pull from the Earth and from the sun on the moon really isn't that different. So it's interesting looking at from the perspective of the sun and then the moon and the Earth orbiting it as separate entities instead of like one orbiting the other, which orbits the other. So just something fun to think about is with these three body problems is that there are stabilities within them, just for very different masses.
Yeah, when I was reading through this, trying to figure out what to talk about today, I actually thought about like that too, because I was like, can I make an analogy for a three-body system? Like, what's a simple three-body system? And I was like, well, the Earth, Moon, Sun, but also it's kind of not a three-body system in some sense, because the Earth, the Moon and Earth are so small relative to the Sun, and even the Moon's so small relative to the Earth that this is like, it's the power of approximating things. It's basically a two-body system. But it's not. But it's close enough to a two-body system that it's, it's way less sensitive to initial conditions. It's not chaotic. I mean, maybe in like billions of years it's chaotic, right? Maybe like the Earth, Moon, Sun system will eventually collapse. Like the Moon gets closer to the Earth every so often. I think I kind of forget, or does it get further? Yeah, Patrick's waving no at me. It gets further from the further away from the Earth. So it's not like, they're not perfect orbits. Things do change, but the bigger, if the Earth and Moon were way bigger, then the system would be probably way more chaotic and things would not be as stable.
Yeah, I sort of off the topic of the solar system, or like but this there's the multi-body system, and here's a crazy. So I sort of hang around these astronomers a lot. We just hang out a lot, and I think just past week I had a mind-blowing. They told me a mind-blowing thing, that's if you take our Milky Way, for example, or most sort of galaxies with they call it the black hole at the center of the galaxy's active galactic nuclei. I don't exactly.
Yeah.
I still have to. I have not yet come to terms with that. But they say that, hey, just take that black hole away, and if you take that black hole away, it doesn't really change the shape and the structure of the galaxy that much, which was wild to me. I mean, just I don't know, maybe being like just a black hole guy, or just my caveman brain thinking, oh, you got the massive thing at the center that's bounding it. But no, really, that's just there for fun. Yeah.
I guess maybe it's like all about the time scales, right? 'Cause if you take away that center, surely something happens after a very, very long time, right? But like maybe on the order of like hundreds of thousands or millions of years, angular momentum's conserved, so things just keep doing their thing for quite a while. Who knows?
Yeah.
Well, also, it's not that it's a super massive. It's not that massive compared to the galaxy, right? Is it a third of the mass of the galaxy? I don't think so. So when the the force go down by 1/r² and the distance that large, I can see why they say like, yeah, it wouldn't change much, because the distance is so large that like it has to be extremely ridiculously massive to be able to influence the galaxy's shape in any significant way, right?
I don't know. I feel like some of these supermassive black holes are stupidly big, but I don't. Yeah,
Yeah, but
I don't
is
know.
it has a mass of a third of a galaxy?
I don't know. I feel maybe.
No, no way.
It do-
There's no possible way.
I'm gonna have to look up on this while we're talking during this episode. I'll come back later with.
Really? You think a black hole can be the size like has a mass of like I don't know a billion stars?
Maybe. I don't know. I don't have any concept of what. I'm a theorist, right? For me, the mass of a black hole is just the letter M. I don't actually
I
think
agree.
about what its
I
actual
agree.
mass is.
I agree. Yeah.
So, okay, just the mass of the Milky Way is estimated to be about 1.5 trillion solar masses. So that's trillion with a T. Sagittarius A star, which is the supermassive black hole at the center of the galaxy, it's about 4.5 million solar masses.
Okay, yeah.
So it's quite a bit different.
I wonder if there's any small galaxies though, like one with super big black hole and not much mass distributed elsewhere. I bet there's a few of them, but yeah, in general, okay.
Yeah, but they wouldn't form the supermassive black hole in the middle, right? Or like that big, like a super massive. Well, how many adjectives can we put on?
Yeah, hypermassive. Yeah. So anyway, this coming back to the article, they figured out with some certainty that this is a trinary system, even though one of the planets or bodies, I'm calling it, because I actually don't know what it is. I'm going to assume it's like a star. It was probably a planet because it's hard to see. Maybe it's a star. I don't know, but it's very far away, and they kind of figured like, all right, this is a trinary system, and it shouldn't have formed if the 9 solar mass black hole in the system collapsed under due to a supernova. So how else could it have formed? So it might help teach us about other ways that black holes can form. Maybe they have different methods of forming, different like this direct collapse mechanism. And maybe there's like, maybe there's other methods that we haven't come up with. We don't know what we don't know, right? Maybe they can form in other ways. So it's an interesting find, I guess.
Yeah, definitely. It's sort of interesting that like you have an astrophysical black hole that doesn't have as much stuff around it as you'd expect it to have formed that way. Maybe just the caveman sense. If you're able to observe the binariness of black hole star sort of spiral, and then also then resolve this third object that's in a Y triple, then there's maybe not so much fog or debris or so and so around the black hole that we would have thought. Yeah.
Yeah, exactly. Like if it went supernova, then there'd be a bunch of stuff around, and also
Exactly.
it would have shot this third thing away. According to like all the models they've done, and they've done a lot of simulations. And the other thing too is that it's a 3-body system. But their current prediction on how long it's been there is about 3 to 5 billion years. And the observable universe is theorized to be 14 billion years old. So it's a fairly stable 3-body system, and that's probably because this third body is so far away. It's like I have a number here somewhere. It's about 300 and what is it again? How do we put it on? Blah. Yeah, it's like 3,500 times the distance between our Earth and the Sun. I think that's an astronomical unit, right? It's very far away, so probably because of that, it's a stable, chaotic system. It's stable over the timescales of that 3 to 5 billion years that they're predicting it's existed for. So eventually, 3-body system. Eventually, something weird will happen to it, but for now, it's still floating out there. Yeah, if you want to learn more about chaos, I think episode 24 we talked about chaos theory, and there's a couple other episodes that popped up in. Like I think in episode 25 we had a guest, Josh, guy I work with, and he probably talked about quantum chaos a little bit there. But yeah, so that I thought that was a cool little paper, an article talking about how. First off, I thought finding I'm sure there's tons of 3-body systems out there. I mean, we know there are. But they're a bit rarer than binary systems, and ones that are fairly stable are probably even rare. So I thought that was cool, and it kind of like this thing that kind of challenged supernovas a little bit. I don't want, because there's tons of evidence that supernovas are a legit thing, but there's a little bit of evidence pointing at other directions. All right, so that was the intro topic, and now we're gonna get to our main topic. We're going to talk to Billy about his research and his past and his hopes and dreams and all kinds of things. So Billy, what do you do? What are you doing at McMaster? What are you working on these days?
Right. So it's black holes. I think it's the main but theoretical physics is sort of a bit broader. And then sort of like, okay, depending on the crowd, so in front of our department, I say, okay, I work on black holes, but on the theory side of things. In front of the public, I say, okay, theoretical physics, it involves black holes, and to grab a bit of like numerical stuff to sort of simulate a few things or solve some mathematical issues in black holes, and to sort of gain some insight. And then in front of my parents, I say, "Oh, it's just computers, guys. Don't worry about it." Yeah, it's kind of hard to explain. So maybe, yeah, I don't know. Was there a specific thing you were looking for?
So you study black holes. I'm just trying to
I mean, that's very all-encompassing words,
Yeah.
right? Like, are you studying the thermal properties of black hole, the event horizon, the gravitational thing, or a gravitational wave, or formation of black hole, effect of black hole around, accretion disk?
You talked about these intersecting surfaces in your research. So what does that even
Yes.
mean? Like,
Okay.
I don't.
Yes.
Is it to do with the fact that black holes can have multiple horizons, or if you have binary systems, their multiple horizons intersect, or something like that? I'm not sure.
Okay. I'm actually glad that Philly actually went off on that and listed off a bunch of things there because it does sort of touch on a bit of them and so maybe I'll talk a little bit about this and we can go back about 50 years or so. That's when that's Stephen Hawking and Ellis. That's the other guy's last name. I just forget his first name. But Hawking and Ellis released a textbook, The Large Scale Structure of Space-Time. So quite a good textbook that a bunch of people still use today. And in that textbook, he sort of drew out a diagram of when two black holes merge, what should it look like? It's called the pair of pants diagram in the community. And that is, it's and whenever we talk about black holes here, it's always sort of perfect black holes. You're writing just the math down. It's just the metric. There's no accretion. There's no mass around it. It's a vacuum solution to Einstein's equations. If anybody, sort of, if that sort of rings a bell better for people. So if you have two black holes coming together, and Hawking and Ellis were able to work out quite well what the event horizons do. The event horizons sort of outline the pants, the pants itself, but in a dynamic situation, what's called an apparent horizon acts differently. So that's sort of the first thing is when you're talking about the boundary of a black hole, you have to distinguish between either the event horizon or the apparent horizon. And I don't know how far into that I should go.
Isn't the typical black hole photograph, or visual photograph, like the image we see from, let's say, you look up, right? Those are not the event horizon, right? Those are like the disk, or like the basically lit up mass that's around it that we're able to see. Is that the apparent horizon, or is it a different thing?
Yes. So I believe the image you're thinking about, the shadow of M87. Yes, that's right. It's the accretion disk that's lighting up sort of the environment around that black hole, and then you're seeing the shadow of it. And yes, and that sort of shadow is sort of implying or suggesting the apparent horizon that you're seeing. If that makes any sense.
I see. So I'm very curious because I don't know too much about black holes. So event horizon is defined by like when the light cannot escape, right? So what makes it apparent horizon? Then why is it so dark if the light can still escape, or is it just a matter of like intensity that we can measure?
So I see. Okay, never mind. I see that I might have given you some false hope with the previous thing with the shadow of the black hole. The apparent horizon and event horizon is sort of a definition issue. I think in pop culture when we talk about light not being able to escape the black hole, I think pop culture, in movies and such, it doesn't say event horizon, but that's not true. So for example, if I asked you guys, you folks here, how many dimensions is the black hole boundary? What would you say? Or maybe let's say how many dimensions is the black hole itself?
It's a
What would
trick
you say?
question.
I don't know. I just want to gauge what the sort of initial thoughts are before I sort
So
of.
I would say like we learned from like relativity, it'd be like 4.
Okay. How about Patrick and Liam?
I want to.
I mean, I would say 4 or 22, depending on which string theory you believe in.
I see. Very good.
But
Liam?
you always, there's this black hole like surface area law or something, and that makes me suspicious of this question.
Okay. What would you say, sort of naively, maybe?
Yeah, I'd say like if I'm an undergrad physicist, how many dimensions is a black hole boundary? I'm gonna say oh my god, I don't know, like 1 plus 2 maybe.
Oh,
Okay,
even none, because this is singularity. There's no dimension
No,
there.
singularity's at the center, not the event or not the surface.
Okay.
Okay.
I'm really glad that we sort of had that sort of little quiz almost.
We've never been quizzed here before. That was awesome. That was
So-
great.
Well, I just wanted to sort of gauge what the sort of initial ideas are so we can expand on that, right? So, okay, so black hole to me, and I don't think there's a right answer, and I have Walden, or General Relativity by Robert M. Wald here, and I'm not entirely sure. Actually, no, I do know how he defines a black hole, and the way he defines a black hole, his black hole is 3 dimensions. So you take your time slice, you take your moment in time, you sort of take a photo of your 3-dimensional world, and then the region in your 3-dimensional world there that is trapped, that's like black, where light couldn't have escaped in that sort of snapshot. That's the black hole in Wald. So that's 3 dimensions. Now an event horizon, sort of by definition, is the boundary of that sort of that 3-dimensional region there is the boundary of it. So that's a 2-dimensional kind of surface, right? Is the boundary of that. But the event horizon is a causal thing, which means that you would have had to evolve your universe, 3-dimensional universe, into like infinite time, see the end state of your black hole, and then trace that back through time. If that makes any sense.
So am I right when I said 1 + 2 dimensions?
You're right in that the event horizon is 1 + 2 dimensions.
Yeah,
That's right.
yeah, because the time dimension plus the 2 for the surface.
Exactly
Oh,
that.
I knew that surface thing was like the trick part of it. I was like, oh, it's got to be like 2D plus something maybe. But yeah,
Exactly.
like
So
also there's different ways you can interpret it too. Like I was just trying to
So
get the question.
so time is not part of it.
if by a relativist's definition of an event horizon, you need the entire history of space-time to define what an event horizon is, because it's a causal sort of surface. It's not simply just the notion of light being able or not able to escape. There's sort of information there and implications there as well. Commonly when we think about light not being able to escape, that's actually the apparent horizon. That's a 2-dimensional object. That's the surface. That's the boundary of a black hole. So that's
the parent horizon's the horizon at a given instant in time.
that's right. So that's simply 2 dimensions, whereas the event horizon is 2.
Okay, and
Right,
right.
so when you say 2 dimensions, I want to clarify, because you can walk on a surface which is two axes, right? That's why it's just 2 dimension.
Yes, that's right.
Okay.
Yes, that's very good. That's a good way to
And
think about it.
can you explain what is a like causality? What do you mean by causal there?
And that is the way I think relativists think about causal things. They try to draw out a space-time diagram, and then they sort of draw events. They say, okay, if an event happened here at this position at this time, is it able to affect another event at this position at this time? And the instances where they can't be what's called causally connected or affect each other is when, in order to have gotten to that position and time that the other event, you had to go faster than the speed of light.
Yeah. So I think when people start learning relativity, one of the first thing you see is a space-time diagram, and usually on the there's like the diagonal lines, which are the light cones, which signifies the trajectory of light. And basically, I think there's one that's like space-like and time-like, right? Like the one that's causally, basically possible. If you want to get from here to here, here to there in the space-time, or if it's gonna take the speed faster than the speed of light, that's not really causally possible or causally connected per se. So anything that's how kind of we divide, like, okay, well, these are events that shouldn't be possible, and these are events that should be.
That's right.
yeah, that's what I was gonna say. Like, it's all about the light cone. Like, if something's outside the light cone and you can't causally reach it, you can't influence it within the limit of relativity. I guess you can. You'd have to move faster than the speed of light to do it, which isn't macroscopically possible. At least there's a whole quantum gravity top conversation we could have there. But yeah, it was cool when you said like, okay, a parent horizon, and then this like the whole event horizon itself is like you trace out the whole history of the parent horizon, I guess. Because like even in like Stephen, like even we're talking about classical gravity right now, but even in like Stephen Hawking's paper, when you derive the Hawking effect, you consider um like vacuum fluctuations from infinitely far in the past near the horizon, and how did they evolve infinitely far in the future. You're considering like the whole horizon's kind of existence, what happened like near when it formed, and you're considering all that kind of stuff, not just like what's happening now. There's different ways you can interpret it, I think, right? But that's one way, I'm pretty sure.
Yeah, that's right. That's right. So yeah, so it's actually, yeah, it's quite important to distinguish between the apparent horizon and the event horizon. And you said something there, Liam, that the event horizon is kind of tracing out the history of the apparent horizon, and that's not always true.
Oh, okay.
In the scenario of static black holes, your black hole doesn't accrete, doesn't gain any mass. It's sitting pretty for all of eternity. That is the case that that your event horizon does sort of is the trace out of your parent horizons throughout all time slices. But in dynamical cases, that's not the case. It's very much possible for us right now to look at a M87, for example, and we're like, oh, we're definitely outside the black hole. We're not inside that horizon. But it's possible for us to be causally doomed to enter its singularity at some point far in the future, where there's a large mass that enters that black hole, and the horizon expands very, very, very quickly, much faster than the speed of light, even. Yeah.
So
So that,
Billy,
yes,
to get a bit back to what you do,
Yeah.
right? Like, so what exactly do you do? Do you do like a theoretical, like develop the the equations for the black holes? Are you doing numerical simulations? Like, what's your work?
And where
good.
does the intersecting horizons come into this too? Like, where does that come in?
Good. So yes, the event horizon, apparent horizon. The apparent horizons of two black holes coming together. You imagine two black holes coming together. It is not. It is. I don't think it's appreciated how two black holes come together. Right. You have two. If you sort of imagine looking at two sort of circles coming together, you might maybe assume that it comes together like a liquid, like the teardrops kind of merger, or this or that. But it's a lot more complicated than that. And the only recently through numerical and because Einstein's equations that they can use to model this black hole merger are highly nonlinear, so it's quite difficult to sort of even do computer simulations for it. And it was only about 5 years ago where a group in Germany was able to work out some of the kinks in the computers and their simulations. And what they found is that in that black hole merger process, you need these self-intersecting surfaces, kind of almost like you can think of them as like the little Klein bottles that they kind of like intersect with themselves and turn on themselves and such. You need these kind of surfaces in order to get the full picture of how two black holes come together. So what we've been doing, or when I started in Newfoundland, Dr. Ivan Booth and his group there, he said, okay, sure, that's the merger scenario, and you had to do numerical simulations and stuff to get your space times, and then you find your black hole boundaries and your surfaces on top of that. But how about for just a normal black hole? If we take Schwarzschild, for example, that one's been known for a while, and that's quite simple. You take Schwarzschild, you try to find these similarly self-intersecting surfaces, and you still find them, and that's not been sort of looked for before. And what these self-intersecting surfaces are is they're black hole boundary candidates. So what's called a MOTS, a marginally outer trapped surface. So then you get into like the definition of what a black hole boundary is. You write down the equations for that. The equations aren't solvable analytically. So what I do is I write down those equations, I derive those equations, and then we numerically approximate them and graph them, and we see that they are self-intersecting. Yeah.
Okay. I want to expand a little bit on the self-intersecting because this is a really fun topological property. I remember seeing something on the client bottle. It's basically a bottle with no volume, right? Because this is self-intersecting. There's no difference between the inside and the outside. There's no inside and outside. Just it's like a weird surface with you want to define a volume in this like a closed space. So it's weird. Is there a good way to explain self-intersection?
Ooh. There are people that I've worked with, including the people in Germany, that'll do a better job at this. But the way I think about it and the way I'm able to sleep at night is if you imagine you're going down a highway, maybe the 401 here in Ontario, and you see there's like a bridge, there's an exit ramp that does a little circle to then go onto an overpass like a bridge that cuts across it. Our self-intersecting surfaces every time you take a slice and you see a self-intersection, it's kind of like that. You're kind of not on the same sort of plane of existence, if that makes any sense. Is that sort of is that crazy or no?
A little bit, but I kind of get what you're saying. Because
Yeah.
you get into these these weird I always think of like a Mobius strip. That's like
It's just one surface continuous throughout the thing.
Yeah.
Right? Usually, if you have a closed bottle, you pick up a water bottle, there's like the boundary where you kind of separate the two surfaces.
Mhm.
But for intersecting surface, you can trace the entire thing, which is like with one surface.
No, I get you. And we've had a lot of arguments in the group of what's inside, what's outside, what's pointing out, what's pointing in as well. So that's unclear, I'd say. And maybe
Yeah, this topology, is kind of confusing, and also like, how do we distinguish between something that's like in principle real versus arbitrarily defined by humans, right? Are distinction between inner and outer surfaces something we made up or something innate to topology? I'm not sure. Maybe someone knows.
Just unrelated a little bit, but so you did all classical gravity, right? Like general relativity and stuff in the past.
that's
Yeah,
right.
but then you came to McMaster, and I know you still do classical GR, I think, but a lot of the people at McMaster, like, Sergey's group and Cliff's group, they're all like quantum gravity guys, and they love that kind of stuff. So you've been probably heavily influenced by them, I'm guessing, over the last few years. And you mentioned in the little blurb you sent me that like you're kind of easing into quantum gravity a little bit, even though it wasn't where you started. So how does that come into this, or like what's going on there?
Yeah. So we're finding it's like when Ivan's group in Newfoundland sort of said, okay, you know what, they found the self-intersecting surfaces. We don't know what they mean yet, and it does keep some people up at night. But that's okay. We find them in just normal black holes. So that was one paper. The short shield black hole. Okay, how about in the Nordstrom case, the charged black hole? That's a different paper. Kerr case, that's another paper. And then we recently did the Kruskal-Sekeres extension, the coordinates, which is it's like a wormhole you can think of. It's like, can we find self-intersecting lots there, or self-intersecting sort of surfaces and kind of related stuff there? We did find some. We don't really know what they mean, but there's another paper. So it's one of those things where take a space time, try to find these self-intersecting things. We find them, paper. It's like a gold mine. So now the next one coming up, and I think it's probably close enough that I can spoil it. The next one is going to be the asymptotically anti-de Sitter spacetimes. And those ones are relevant when you talk about the ADS-CFT correspondence.
So what is that? Just as a refresher for me, but also for anyone who might not know.
Yeah, so I can't say too much about it. I'm still trying to get through this book about it. Um, but the idea is back in 1998, Juan Molesina, the most cited theoretical man in history, probably there's a lot of citations for him now, had released this paper that said, "Hey, check this out. In this limit, you can you can say you can correspond stuff on the geometry side to a conformal field theory side. So, for example, if you take the area of something on this geometry thing on the corresponding sort of field theory, you can talk about its entropy. And sometimes when you're talking about like sort of field theory or like a scenario where you have many particles or this or that, it might be hard to calculate. So it's sort of this dictionary that, okay, you can actually just revert to the geometry side, do an area calculation there, which is a lot simpler, and then infer sort of entropy, temperature, other thermodynamic properties from the CFT side.
So
And
could
and
you
that's
explain briefly, like what is ADS and what is CFT? So someone, let's say,
So CF
coming in like not knowing science well, law of
for
physics,
sure.
these things.
For sure, yeah. So space times is like sort of this Einstein's theory of general relativity. You take geometry and you sort of infer gravity and other dynamics from it. And and um and the black hole solution, the most simple one, the Schwarzschild solution, that's asymptotically flat. That's what it means. You have the black hole, a lot of curvature in the middle, but then as you go further and further away, it's flat. So then you're not affected by gravity. If you're in what's called an asymptotically de Sitter spacetime, you have that's an expanding universe. So if the black hole, it curves in the middle, that's fine. You're closer to the black hole, you feel the gravitational effects. But as you go further away from the black hole and just sort of towards um, infinity, you feel you're actually accelerated away, and like you're in this expanding universe. And anti-de Sitter is the opposite. You're in a contracting universe. As you try to go further and further away, there's this sort of there's the geometry is sort of pushing you back in. So that's the ADS part. So it's really just purely geometry. It's just how it curves towards the outside. Um, and then whereas the CFT part, well, that's related, and I won't say too much things here because I don't want to say something wrong, but that's related, and that's sort of that's related towards the quantum field theory side. So Juan found this dictionary between the two, not exactly the union of quantum field theory and gravity, but this dictionary between the two in this limit, that sort of works.
I see. I don't know almost anything about CFT. I think like I see this term a lot, ADS CFT. I heard de Sitter space, whatnot. I never really studied it, so that's good to. It's interesting to hear the definition of it, and also don't we know that the universe is expanding at accelerated rate? So that in a sense the ADS is not true, or is that a
Good.
different thing?
No, you're absolutely right. You're absolutely right. Yes, that's right. That's right. So why anti-de Sitter? And really, I think the only reason we're focused on the anti-de Sitter case is because this ADS CFT has been so successful. Like I believe they've tested it. I'm gonna say it wrong, but there's been results that Hawking, like those sort of results, right? The Bekenstein-Hawking sort of black hole thermodynamics stuff, or black hole dynamics they call it, that's been sort of tested, and you see sort of, oh, you kind of get the correct results that you want. So that's it's been tested with a bunch of these sort of thermodynamic ideas with regards to black holes and geometry, and it's sort of the numbers sort of add up, and it seems like it's good. So that I think that's why they're so focused on this ADS CFT. It's been quite successful in just checking
Oh,
some
so
numbers.
you said for ADS, the universe it's contracting. Then you said like
That's right.
asymptotically is getting slower.
Asymptotically contracting.
Or,
That's
but
right.
is the universe asymptotically
Ex-
expanding, or
That's right. That's right. So they have tried to make some DS CFT correspondences, but I believe that there are issues with some of them. I don't know exactly what is it, but there are issues. It's not as clean and beautiful as the ADS CFT one.
So you're saying the ADS-CFT that we have is nice and beautiful, but what we found in terms of the experimental evidence is the opposite of that?
Yeah, or that we need to find a de Sitter de Sitter CFT correspondence so that we can apply it to our own universe. Yes.
Okay, but if the universe were to form in the ADS-CFT, we would have a good mathematical framework to work on that.
Yes, and then maybe even run some experiments and see if if stuff actually works. The
They need to
theory.
understand the easy one before they can understand the hard one, kind of
Oh,
thing.
that's a good way to put it.
Yeah.
That's a good way to put it.
So pivoting, I wanted to ask you about how you got into science. So, like you did kind of black holes for your research since your undergrad, but like what got you interested in kind of general relativity, and what got you interested in pursuing physics in university? Were there any like experiences in high school, or were you just always interested, or what, or did you not know until you kind of ended up there what was going on?
Yeah, that's actually I know the answer. There's a Tom and Jerry episode, The Mouse and the Cat,
Yes.
where Tom on a snooker table, like on a pool table, he has this giant contraption trying to catch Jerry, like a pool ball, like hits the button on a fan, then the fan starts up, and then there's like a boat with a sail that like moves towards something else, like a spatula that whacks Jerry or something. And I remember that being maybe like one of the first catalysts, and then also just having Legos and stuff like that. And then so that was maybe like, okay, going through school, I was just more interested in science and really much affected by TV shows. I think like Meet the Robinsons, one of those that movie where like the kids like the inventor
Mm-hmm.
and make some gadgets and stuff, right? Like that was very cool to me. And then in middle school and high school, um, I was not a Star Trek guy. I was not a Star Wars guy. I was a Battlestar
Oh, I
Galactica
love
guy.
Battlestar Galactica. Yeah.
Yeah.
Okay.
What drew me in, I think, was the fighting, the Vipers, the plane scenes. In space, you can't use control surfaces. You can't, have flaps and stuff to maneuver. You need what are called RCS thrusters,
Mhm.
little bursts of air to have you roll and maneuver and such and such. And I think that was the only show that I saw that had that. You had like a little poof, 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 and there it's not just guns firing. It's sound effects for them maneuvering around too. So I love that, and I remember just seeing the faster than light travel scenes. And I thought, that'd be cool for us to have faster than light technology. So yeah, so going into Calgary, I was blessed to have gone to Calgary as an international student, but under a scholarship by the university. I very much was thinking, I'd like to do something that can progress us towards some sort of faster than light travel. And well, if there's a hard limit on the speed of light, or on the universal, if there's a universal speed limit that is light, and that's sort of been postulated by Einstein. Let's follow in his footsteps, do some gravity, and see if we can break it.
So
So that's sort of
since you started, right? For FTL stuff, are you more hopeful or less hopeful now that you know more physics?
I already know the
man.
answer to that.
I'm less hopeful, unfortunately.
Yeah, we kind of realize how so limiting it is to the speed of light is, and there's so many tricks people try to pull, both theoretically and experimentally, but none has been successful so
Yeah.
far.
Well, we have to reach like 10% the speed of light before we can even start worrying about faster than light travel. Right? Like we still got a long ways to go.
You're not even close.
Yeah.
I'll be happy at 50%.
Yeah, well, man, even like 5%, 10% would be like pretty nice. That's like that'd be pretty acceptable, I think. It's such a hard limit, right? Like you said.
it's a very high goal too, and I know as when we were young we always have like, we're gonna solve this huge problem like in physics, and and sometimes those problems seem to be a very a steel wall, right?
Yeah, well, it's like also like, we were interpreting the speed of light as a problem that could be broken when it's like pretty much just the way it is. It is what it
Just
is.
axiomatically defined as a constant.
Yeah, I mean, there's like, Lorentz violating theories and things like that, but they're nothing to do with like, can we get a spaceship to go faster in light? There's like warp drive and wormholes and theories and things like that, but they're also like difficult and not easy to achieve theoretically. But yeah, so that's pretty cool that you got into science because of that. Like, it's always cool. You hear a lot of physicists they got motivated by TV shows and movies. Like you said, a lot of people like Star Trek. Like I know physicists who got into it because of Star Trek. You got into it because of Battlestar Galactica and some other things. You're the first person I've heard say Battlestar Galactica was your motivation, so that's interesting. But that's cool.
Yeah, I think also like TV shows are, in a sense, like they're not made to be realistic, right? But it is invoke a lot of imagination of what could be. To me, like I never really watched Star Trek, Battlestar. Star Wars to me is like I don't. It's not raw science for me, but to me it's like Halo. Halo was the space thing for me because it's super cool. Come on,
Yeah.
jumping this USS forward onto Dawn, and it's just amazing.
Yes. Yes. That's right.
Yeah. So, to go back down the memory lane a little bit, were you always interested in science growing up as as a kid? What or you think is more, or is it more like a school thing that may got you into science, or you just like a curious person? What's that like?
Um, yeah, I mean, I was brought up in like my mom is like Asian, right? So very much grew up like make sure you do something that you're good at and you're useful to
Do you grow
society
up in
kind of thing.
Canada?
I grew up in Hong Kong. I was born and raised in Hong Kong. And my mom is Thai, so she moved from Thailand to Hong Kong. Met my when my birth father had me, and then like separated. My stepdad came in very early in my life. So and my stepdad is American, so that's why I don't speak with much of an accent because he trained me up well.
I see, and
um,
in Asia, it's very competitive. I grew up in Thailand, and the academic competition is quite extreme. And compared, I don't know about too much about here, but from who I teach and from what I hear about my friends here, it seems like it's not as much pressure. So, was it like that in Hong Kong too, where this like you want to go science, everybody is like reading books?
oh, that's right. Yes, that's right. I mean, yeah, very very high. I was lucky in that I went to what's like a it wasn't the government school.
The
It was sort of
international
like
school.
yeah, that's it. What we call international schools or private schools. That's right. So it was the American International School in Hong Kong there, and so only spoke English. So yeah, the curriculum was the American based, but the social pressures were still there. It was very much everyone, most people, most of my buddies were Asian, so it was very much you need to keep those high grades in order to get into the very competitive universities in Hong Kong and that
Do you go to cram
so
schools? There are probably a lot of cram schools around too, right?
there are, yeah, but I didn't go to any. My school was or I think early into my high school years I knew I wanted to come to Canada, so I already knew I already knew I wanted to go to Calgary. I think I had visited there with with a friend who um who brought me there one time, and I saw the mountains, and I thought, yeah, this is the place for me. So no, I didn't go to cram school, but a lot of my friends did. A lot of my friends did.
I wonder, like, okay, do you find it the undergraduate experience how you find it in terms of difficulty? Like, is it like much different? Do you think?
So here's what I think about the academics between like the Asian region and North America. I think in Asia it is higher pressure and maybe it's not fair for kids, but I think high school and junior high is well it's better is not the right word, but people come out more. I don't even want to say competent, but they come out sort of maybe more confident with mathematics, right? Like
Yeah,
they
the way
do.
I like to put it is that I think in Asia we are more focused on the top 1%, where people who can really pass and do well, they're very good at it because they went through all these examinations and all these
Yes.
like tough things. But a lot of people who really can't do it, like they're not gonna be able to. I think the average for a national math exam my year it was like 6%, something like
Oh
that.
wow.
It's ridiculous, right? And people who are
Yeah.
good at it, they got like 99%. It is
Yeah.
so
Yeah.
much gap or this disparity between who are good. While I think what I see here is more level out.
Yes. Yes. It's a bit. Yeah. Um. Yeah. So for example, in my graduating class in high school, I think I was average. I was middle of the pack, but I think my sort of grade average coming out was still like 86% or something. And that was middle of the pack, right? It's out of like 70 kids, which means that the 35 students like above me, they went on to do like they went to bigger, really prestigious schools around that area, and I think one person went to like Harvard for an undergrad. Um, so yes, but then with the undergrad experience, difference between the two regions, I really I I'm a big supporter of the North American style more. It's a bit more free to like you're freer to think in a way, whereas over there it seems like this is for my friends and I don't think this is like a good representation, but it's for my friends that I've seen go through it. It's a bit more sort of not restricted, but like controlled. There's not much freedom of thought. It's like do these questions like physics for example. Do these questions and just sort of memorize and know how to do them and don't really understand them.
Yeah.
But that's maybe not a good representation
Well,
because
there's more emphasis
yeah,
on the creative spirit here, I find, because let's say you want to solve a problem, and a lot of times I think back home it's like, here's how to solve it, know it, and you will solve this specific problem. But when you translate into real research or real problem solving, that's not true, right? We don't have a recipe for solving a lot of problems, and be
that's right.
able to think creatively is an asset that we need to develop, which sometimes it happens to some people. Some people will learn that way, but I don't think it's like the greatest way to teach students to just knowing the recipe book.
Yeah.
So we're running out of time. So before we get to our story, what are Billy? We always ask guests this. Feely started doing it, so I will continue it today. What are your hopes and dreams? I mean, Feely, you can ask them. Like you ask better than I do. Like,
Well, where do you see yourself in the future? I'm not really talking about 10 years, 15 years, no time scale. Do you see yourself being a theoretical physicist or a cosmologist? Or you see yourself teaching? Who do you see yourself being? Are you going to be the scientist to solve the fastest that light travel? Where do you see yourself in the future?
Yeah. I have two paths that I see. There's a dream path which is to be a professor at the University of Calgary, a theoretical physics professor. I really I love that city. I'm now a Canadian, so and I call myself a Calgarian. That's just how much I love that city. So that's the dream, and I think we all know how difficult it is to get a faculty position anywhere.
yeah,
So, uh, yeah. So that's the dream. But but then but then I'm okay settling for anything else as long as it's in Calgary. So it's if whether I'm teaching, whether I'm out in the industry applying it to like data science jobs or whatever it is. Yeah, so that's what I see in the sort of near and far future.
All right. But okay, if one day you have something like an auto job that maybe not specifically solving GR or these type of thing, like are you more into, or are you more into like things that like, okay, I really want to solve this problem, I want to solve this gravity thing, or are you see yourself doing something else that's like unrelated to gravity?
Ah, yes. I see myself doing something else. I don't see I get what you mean, like an ultimate question that I want to answer. Um, Yeah, I don't see it. I see myself as like a cog, right? Like if I'm able to in my lifetime make any incremental progress for us as a human race to develop like an understanding of the universe, any like infinitesimally small increment, I'm okay with myself. Like I'm happy with my life to have done that.
Yeah. I think I see it pretty similar too. I think when we were young, we see this big problem. Like, okay, I'm gonna spend my life solving this. And I think in history of mankind, maybe 100, 200 years ago, those type of I don't know career paths is more prominent. It's like, okay, this guy just sit down and just solve this for 50 years of his life. But now, I think because the world is more open, we see a lot more career paths or things that we could do, and we see the amount of research that's being done in the literature and how like infinitesimal one's contribution is, unless you're Einstein or someone like that, right? That's a big and and these days I don't mind being the cog in the machine because it helps the machine moving, and that's why I like doing like computational work because it's you like analytical work is nice and pretty, but sometimes it takes a lot of time to mature and it might not even go anywhere. But there are a lot more systems you can solve numerically. Like you said before, your equations are linear, it's complicated. If you were to find a close analytical solution to that, good luck, buddy, right? But you can do numerical work and say, here's approximately what it is, and it's usually quite useful.
Yeah. Yeah.
Well, thank you very much for joining us, Billy. That was great to hear about your work and your past and all kinds of black hole things. Very eye-opening. So thanks for coming.
Oh, yeah. Thank you guys. This
Yeah,
is
it's
fun.
a good little,
Yeah, thanks for
good
coming.
little talk, isn't it? So to end off the episode, Patrick is going to tell everybody how they can reach us, and then he'll end it off with a story potentially.
Okay, so if you are interested in reaching out to us, whether you would like to be a guest on the show or if you have questions about what we discussed on the show, there are a couple different ways that you can do this. The first is our email, so you can find us hyperthesispodcast@gmail.com. You can send us questions, queries, concerns, comments, or if you're an expert in your field, much like Billy is, we would love to have you on the show. We are also on Instagram. You can find us at the Hyperthesis. We post updates. We just released, at least as the time of recording, we just released our first episode for the season. So you can find out updates there. There are some fun pictures and other information that we do post on the Instagram. And of course, you can send us a DM. Now, if you're interested in asking questions about Billy's research or anything specific to that, do you have a good way that people can contact you?
Yes, I do have a online presence, like a website, a homepage. That's ktbsievers.ca, and yeah, my contact information is on there as well.
Perfect. So if you have questions for Billy or are interested in his research or past research as well, feel free to check out the website, which is linked in the notes down below. If you have found us, congratulations. You're listening to us, so you must have found us. But we are based out of many different platforms, including Spotify, which is kind of our home base, YouTube Music, Apple Podcast, Audible, and we're also on YouTube as well. So you can see very nice animations from our videos, and hopefully we'll be getting decently up to date with our newest season, depending on how much Feely wants to mistreat his MacBook. So whether you have questions for us or sharing us or whatever, check out some links in the notes down below for Instagram and YouTube channel, as well as past episodes, which we've brought up. And then if you're interested in contacting Billy, please check out the website, also linked down there. And again, if you're an expert in your field and would like to be a guest on the show, we would be more than happy to have you on. Just reach out to us. And so to finish off today, I want to talk kind of adjacent to the discussion, and I'll be quick about it because we're going a little bit over our usual time, but that's okay. So today's story will be based on a very famous physicist, which at least the four of us have all heard of, and I'm sure anyone who's done any type of physics degree or even kind of higher end high school courses, or really has worked in a few different fields, they'll have heard about this physicist who whose work was used a lot for especially contemporary groundbreaking research. But this physicist's work really has affected many different fields, from cosmology to particle physics and just many areas in between. His work is said to have, quote, prepared the ground for the fruitful reception of the new ideas based on quantum theory, end quote. He was regarded as the world's leading spirit by theoretical physicists and even won the Nobel Prize in Physics. His work transformed the world, and if you haven't guessed on that little pun, this physicist was named Hendrik Anton Lorentz. Now, way back in episode 20, we talked about the work done by Lorentz. That's our part 1 of our special relativity series. So feel free to go back to that episode, which is linked in the show notes as well, to hear more about his work. But today we'll be focusing a bit more on his life and some of his major achievements and accomplishments throughout. So to start, Hendrik Lorentz was born in the Netherlands on July 18th, 1853 in Arnhem. His father, Gerrit Frederik Lorentz, was a well-known horticulturist, while his mother, Geertrude van Ginkel, she unfortunately died only when Lorentz was 4. He did have a stepmother from the age of 8 onwards, but he had his kind of own free thoughts that he went off of. And from that free-thinking behavior, especially in terms of religion, as well as a very bright young mind, he really excelled in what he did. So he was very fortunate during his early school years and high school especially, that at the time the Netherlands had implemented a new, essentially, high school system in his hometown of Arnhem. And so he was able to start off in a 6-year program or 5-year program, depending on who you ask, in year 3. So he graduated quite quickly. And not only did he excel in physics and the physical sciences as well as mathematics, he also excelled in English, French, and German. So he was multilingual to start. And at the time, to get into an Netherlander university, you were required to pass an exam in classical languages,
You mean like
which
Dutch?
of course he passed.
Like Dutch University?
Yes, Dutch University, I guess would be a good term for that. And the Dutch university that he went to was Leiden University in Leiden, the Netherlands, where he earned his bachelor's degree in physics, where he was heavily influenced by Friedrich Kaiser. Now, it is very notable. He started university in 1870 at Leiden and graduated in 1871 with a bachelor's degree. So he did his bachelor's in 1 year, which we see more often. Kind of at that time, there was, I guess you could say, a little bit less structure there. But afterwards, he returned to his hometown in 1872 to teach a night school in mathematics while preparing for his doctoral thesis. Now, his thesis itself focused on the reflection and refraction of light, and he worked under Peter Ricke and really refined the work that was done by James Clerk Maxwell. In 1875, he earned his doctorate degree at the age of 22. And less than 3 years later, at the age of 24, he took the position as the chair of theoretical physics at the University of Leiden. Now, just that position, again, there's a little bit of fuzzy details around this, but some accounts say it was created just for him. However, other accounts say that it was first offered to Johann van der Waals, yes, that one from van der Waals' force, but he had taken a position elsewhere, therefore letting Lorentz take the position, and there he stayed at the University of Leiden in one form or another for the rest of his life. So he was involved with that university from the very start of his, I guess, physics experience all the way to the end and his death. Now, during his many years at Leiden, he made an innumerable amount of accomplishments. Again, we've talked about a few of them before, especially in relation to relativity. But with his work on electromagnetic phenomena, especially with reflection and refraction of light, he thought about how things move in reference to what at the time was the proposed luminiferous ether, which we now know isn't really a thing. But he discovered from his thinking the idea of reference frames and how you can convert from one reference frame to another in respect to this ether. So check out our special relativity episode for more on that. But essentially, these ideas really created the groundwork for relativity itself by looking at different reference frames, how we can explore and convert between those different reference frames, and then also kind of how bodies are able to move and contract and expand in different directions. So again, this was kind of all in the field of working with this luminiferous ether, but again, that was proven not to really be a thing based on the Michelson-Morley experiment. But this is a foundation for a lot of his work with looking at reference frames and then additionally time dilation. And this laid the groundwork for Einstein to come up with the theory of special relativity and then go on later for general relativity. So with Einstein's theory in 1905 of special relativity, in his paper entitled On the Electrodynamics of Moving Bodies, well, today we call it the special theory of relativity. It was originally called the Lorentz-Einstein theory because of Lorentz's pivotal work that contributed to it. Now, I wouldn't get too much into that again. There's a lot of history that goes into special relativity itself. But I do want to kind of focus on one other thing that Lorentz is known for, and that's his work on the electron. So it's very interesting to learn that the 1902 Nobel Prize, which was awarded in part to Lorentz, was actually based on his predictions that electrons existed. So it's very interesting to read about the fact that he proposed that within atoms there were these charged particles that must have existed. And so based on that theory, Lorentz worked with Peter Zeeman for his discovery and explanation of the Zeeman effect, which is the effect of splitting of a spectral line into several components. And again, relating back to his work with light and reflectance and refraction, Lorentz was really the first to kind of state the idea that those charged particles within an atom were the ones that were producing light through some sort of oscillation. So just incredible work and a very well-deserved Nobel Prize in 1902, which was again shared with Peter Zeeman for the Zeeman effect. But his list goes on of his contributions from the theoretical side of physics. A couple other notable things from his life around that same time. So Lorentz married Aletta Katharina Kaiser in 1881, so 21 years before he won the Nobel Prize. And they had 2 daughters and a son from the marriage, and one of those daughters went on to become a physicist as well. Now, in 1910, Lorentz found that the role of the chair of theoretical physics at the University of Leiden was too much work and too much time away from research. So he actually resigned from that role, became an external professor, or what we might maybe call an adjunct professor today. And he took the position as the curator of the physics cabinet at the Taylor's Museum in Haarlem in the Netherlands. Now, he still gave lectures at the University of Leiden, including what became known as his Monday morning lectures, where he introduced new topics in theoretical physics. But to actually fill his old position as chair, he first went to Einstein, who had just accepted his position at ETH Zurich. However, Einstein later said that he had no regrets about this because he was scared of trying to fill the shoes of Lorentz. Paul Ehrenfest eventually took that position, and the Institute for Theoretical Physics, which it was then named, became known as the Lorentz Institute. So Lorentz, after taking time away from his duties within the university, also became more involved with the civil service, especially after World War I. He has a couple notable opportunities and initiatives that he implemented, including he was the driving force behind a government program that was using kind of science and research to look at issues like food shortages, especially after World War I. However, that didn't meet too much success, but he did work on hydrology and hydrodynamics, and especially in a place like the Netherlands, where it's surrounded by water and they rely on a very interesting system of dams and floodgates and all that to protect the country and to take back some of the country to land. He actually spent 8 years working on building up hydrodynamic equations from their most basic level to try and make numerical predictions about water flow, especially in a tricky body of water bordering the North Sea. And those numerical predictions from him were, and again, at the time, it was reliant on human computers, not actual computers. They were found to be quite accurate. They were able to build a kind of floodgate in the area, and one of the locks in that area is named after Lorentz. Now, not too long after finishing his work on hydrodynamics, Lorentz suffered a short, very serious illness, which eventually led to his death on February 4th, 1928. He was so influential in the Netherlands and in physics that there were 3 minutes of silence held in the Netherlands for him on his funeral day, with telephones and telegraph services being suspended during that time. Some notable attendees to his funeral, which is actually, the procession is available on YouTube. It's one of the kind of first recordings that's being digitized now of this type of funeral procession. But some notable attendees include Einstein and Marie Curie, along with a graveside speech given by Ernest Rutherford. Now, Lorentz leaves behind a massive legacy, which is still felt to this day and is even used in everyday life. Think about the GPS satellites that need some corrections up there to make sure that everything's on time and you're going to the right place. But it's really hard to state the presence that his work has in both the physics community and in, a lot of other areas of science. So instead of really going over his full legacy, which I think would be a whole episode on itself, I just want to read 2 quotes from one of his contemporaries. The first quote from 1928, which occurred not too long after his death, says, quote, "The enormous significance of his work consisted therein that it forms the basis for the theory of atoms and for the general and special theories of relativity. The special theory was a more detailed exposé of those concepts which are found in Lorentz's research of 1895. End quote. This was said by Einstein not long after his death, and in 1953, Einstein would later say of Lorentz that, quote, "For me personally, he meant more than all the others I have met on my life's journey," end quote. I mean, that's coming from Einstein himself, and the fact that he's a household name and Lorentz isn't, I don't think sits well, because Lorentz should definitely be up there, because he's truly a giant whose shoulders that other giants have stood on and have a good, solid base on.
Wow. What a story. All right. Thank you very much for that story, Patrick. That was a great one. And thanks again, Billy, for joining us. That was a great episode. A little longer than they usually go, but that's not a bad thing necessarily. So we'll see everybody next time. Have a good one.
Take care.
Bye, everyone.
Bye.